Welcome to our lesson on setting up a hypothesis test for a population proportion. This is a foundational topic in AP statistics, and by the end of this video, you will be able to identify the correct testing method, define the population parameter in context, state the null and alternative hypotheses, and verify the necessary conditions for the test. We are moving from simply describing data to making formal inferences about a whole population based on a single sample. Let's get started. When we want to make a decision about a population based on sample data, we use a formal procedure called a hypothesis test. Specifically, when we are dealing with categorical data, like yes or no responses, we use a one-sample z-test for a population proportion. The first step is always defining our parameter, denoted by the letter p. This represents the true proportion of the population that has a certain characteristic. To properly identify the parameter, you need to hit three key points in your description: the population parameter itself, the response variable, and the population in context. When you write this out, you must be specific. Don't just say P is the proportion. You should say something like P is the true proportion of all students at this high school who prefer online textbooks. Notice how that includes the variable, preference, and the context, all students at this school. Once the parameter is defined, we identify our method as the one-sample z-test for a population proportion. This name tells us we have one group of data and we are using the normal distribution, or z-scores, to make our decision. Now, let's talk about the claims we make. In statistics, we always start with two competing statements: the null hypothesis and the alternative hypothesis. Think of the null hypothesis, written as H0 or H0, as the status quo. It is the claim that is assumed to be true unless we have very strong evidence against it. In a test for a population proportion, the null hypothesis always uses an equal sign. Here, P0 represents the claimed or historical value we are testing against. On the other hand, the alternative hypothesis, HA, is what the researcher actually suspects is true. This is the claim we are looking for evidence to support. If we think the proportion has increased, we use a greater than sign. If we think it has decreased, we use a less than sign. These are called one-sided tests. If we just want to know if the proportion has changed in either direction, we use the not equal to sign, which is called a two-sided test. Remember, hypotheses are always about the population parameter p, never the sample proportion p hat. We already know what p hat is from our data. The mystery we are trying to solve is the value of p. To make sure our conclusions are valid, we must check three specific conditions before performing the calculations. Think of these as a safety inspection for our statistical test. The first is the randomization condition. The data must come from a well-designed random sample or a randomized experiment. This is crucial because it ensures our sample is representative of the population and helps us avoid bias. The second is the 10% condition. When we are sampling without replacement, our sample size, little n, must be less than or equal to 10% of the total population size, big N. Technically, this allows us to treat the individual observations as independent, even though the probability changes slightly with each person we pick. The third is the large counts condition, which allows us to use the normal distribution. We need to expect at least 10 successes and at least 10 failures based on the null hypothesis. Notice we use P0 here, the value from the null hypothesis, because we are performing the test under the assumption that the null is true. If both of these values are at least 10, the sampling distribution of the sample proportion will be approximately normal. Let's apply these steps to a real-world scenario. Suppose a national survey claims that 45% of all adults in a certain country exercise for at least 30 minutes every day. A fitness researcher believes the actual proportion is higher than this. The researcher surveys a random sample of 150 adults and finds that 78 of them exercise daily. First, we must define the parameter. P equals the true proportion of all adults in this country who exercise for at least 30 minutes daily. It's important to include the word true or population and the full context to be precise. Next, we identify the testing method. Now, let's state the hypotheses. The null hypothesis is the nothing is different claim, which comes from the national survey. The researcher's claim is that the proportion is higher. This makes it a one-sided test. Take a second to look at that. Notice how both hypotheses use the same value, 0.45, and they both use the population parameter p. Before we could move on to calculations, we would need to verify the conditions. 1. Random. The problem states a random sample of 150 adults was taken. Condition met. 2. 10%. Is 150 less than 10% of all adults in the country? Yes, it is safe to assume there are more than 1,500 adults in the country. Condition met. 3. Large counts. We use n times p naught, that's 150 times 0.45, which equals 67.5. Then 150 times 0.5, 67.5 is greater than or equal to 10, and 82.5 is greater than or equal to 10. Since both expected successes and failures are at least 10, the normality condition is met. Let's try a second example to see how we handle a not equal to alternative hypothesis. Imagine a candy company claims that 20% of their chocolate candies are blue. A student suspects that the proportion is different than 20%, so they buy a large bag of 200 candies and find that 32 are blue. Step 1. Define the parameter. P is the true proportion of all blue chocolate candies produced by this company. Step 2. Identify the testing method. The method is a one-sample z-test for P. Step 3. Set up the hypotheses. The null is the company's claim. H0 is P equals 0.20. Because the student just said the proportion is different, we don't assume a direction. This makes it a two-sided test. Now, let's check the conditions for this scenario. First, random. The student bought a large bag. Is this a random sample? In AP statistics, we usually need the problem to explicitly state it is a random sample. If it doesn't, we must state that we are assuming the bag is representative of all candies. For now, let's assume it's a random sample of candies. Second, the 10% condition. Is the sample of 200 candies less than 10% of all candies produced? Yes. The company likely produces thousands of candies. Condition met. Third, large counts. We multiply the sample size 200 by the null value 0.20. 200 times 0.20 equals 40 successes. 200 times 1 minus 0.20 equals 160 failures. 40 is greater than or equal to 10, and 160 is greater than or equal to 10. Both are greater than or equal to 10, so the normality condition is satisfied. This means we are clear to proceed with the z-test. Let's look at one more example where the conditions might be a bit tighter. A local politician claims that more than 60% of residents support a new park proposal. A reporter, skeptical of this high number, conducts a random poll of 40 residents and finds that 22 support the park. First, we define our parameter. Our method is once again a one-sample z-test for P. Now let's establish the hypotheses. The claim being tested is the politician's statement. The politician claims the support is more than 60%, but often in research, we test the claim itself. If we want to see if the politician is correct, our alternative would be, now we must be very careful with the conditions here. 1. Random. The reporter conducted a random poll of 40 residents. Condition met. 2. 10%. Is 40 less than 10% of all residents? Assuming the town has more than 400 residents, this condition is met. 3. Large counts. Let's check the math. N times P, 0 equals 40 times 0.60, which equals 24. N times 1 minus P minus 0 equals 40 times 0.40, which equals 16. 24 is greater than or equal to 10, and 16 is greater than or equal to 10. Even with a smaller sample size of 40, both the expected successes and expected failures are at least 10. This means the normal approximation is still valid. Notice a common mistake. Students often want to use the sample data, 22 out of 40, to check this condition. Remember, for hypothesis tests, we check the conditions assuming the null hypothesis is true. So, we always use the value from H0, which is P minus 0. To wrap up, let's review the essential steps for setting up a hypothesis test for a population proportion. These steps are the foundation for everything that follows in statistical inference. First, define the parameter P in context. Second, identify the test as a one-sample z-test for P. Third, state the hypotheses, H0 and HA. And finally, verify the conditions, random, 10%, and large counts. We learned that the parameter P must always describe the population and the variable in context. The appropriate method is the one-sample z-test. We saw that the null hypothesis, H0, always uses an equal sign to represent the status quo. The alternative hypothesis, HA, uses greater than, less than, or not equal to, depending on the researcher's claim. Finally, we covered the three critical conditions. The data must be random. The sample size must be less than 10% of the population to ensure independence. and we must have at least 10 expected successes and 10 expected failures, using the null value to ensure the sampling distribution is normal. Can you identify why we use p-hat when checking the large counts condition? Take a moment to think about that. We use p0 because a hypothesis test is a what-if scenario. We are asking, if the null hypothesis were actually true, how likely is it that we would see a sample like ours? Therefore, we must build our model based on that null value. You are now ready to set up your own tests and ensure they meet the rigorous standards of AP statistics. In our next lesson, we will move beyond the setup and learn how to calculate the test statistic and the p-value to reach a final conclusion.